Let's now go through the steps that are involved in creating regressors, which we will eventually enter into our design matrix. To do this, let's consider a simple example. This is one of these types of experiments that were used in the early days of neuroimaging. So we have a block design here, and in each block we present different types of stimuli. So first type of stimulus would be a chromatic circle with different color shades here, of blue in this case, and then in other blocks we present achromatic types of stimuli. So we present them repeatedly, as is commonly done in block designs, with the different conditions, so chromatic, achromatic, varying randomly throughout the experiment. Note also that there is sort of an off period here, which is this rest condition where we just have a central fixation cross to allow the bold response to go back down to baseline. So this is an experiment that would allow us to study what the neural correlates of color perception are, by contrasting chromatic to achromatic in this case. Now, the first thing that we need to do when we construct regressors is we need to know our on and off times, and they have to be synchronized, obviously, to the bold responses or to the fMRI time series. So by on and off times, I mean when do subjects start seeing the chromatic stimuli and for how long? And then the same thing is true for the achromatic. When do subjects start seeing achromatic stimuli and for how long? So regressors are basically constructed based on the information that we have about the experimental design. So the types of things that as experimenters we can manipulate. What do they see, and at what time points do our participants see these types of stimuli? Or what tasks do they do, and at what time points and for how long do they perform these tasks? That is basically how we construct these boxcars here. Now, of note, we have two experimental conditions in this simple experiment. We have chromatic, we have fixation, and we have achromatic. Fixation actually goes into the baseline parameter of our model. So we're not interested in modeling this. This is implicitly modeled. But we're interested in modeling chromatic, which is the first regressor here. So we have these boxcars. So at 7 seconds this goes on, and at, let's say, 15 seconds this goes off, right? So we have these types of boxcars for two regressors, chromatic and achromatic. You can see that we now created two different time series for this very short and simple experiment. C and A, so chromatic and achromatic. But these regressors do not yet, their boxcar functions, they do not yet take into account what we know about the shape of the hemodynamic response function. So what we do is we convolve these regressors, these boxcars, to with this hemodynamic response function. This is a simple multiplication function of two different functions, and we get this new response that is much closer to the hemodynamic response that we should expect to see in different brain regions. So we're passing it, in a sense, through an HRF filter to account for the lag and shape of the hemodynamic response, which is the basis of our measure, the bold signal. Now we have these convolved regressors, so we have C and we have A, and we can enter them actually into our design matrix, into our model. And the next step then is to check or to estimate to what extent each voxel in the brain follows one of these expected shapes. So to what extent the bold response in each voxel follows the predicted signal. So we're comparing the observed signal. Say this is our observed signal here. This is a simulation, obviously. And we're comparing it to the predicted signal, namely to two regressors. So each voxel will have a beta value for chromatic and a beta value for achromatic. That indicates how well the predicted response to each of these stimuli is followed, or predicts the actual observed bold response in each of these voxels across these two stimuli. So there will be two separate beta values, one for chromatic, matching this shape to this shape, right? Matching, or it's a correlation analysis in a sense of the predicted response with the observed response, and a second correlation analysis of the predicted response with the observed response, but accounting for each other, obviously. So here's an example of this kind of match. We can simply overlay these two. So we have the predicted response in purple and the observed response in Y. And you can clearly see that in this case, which in real life rarely occurs, almost never this well, the observed waveforms are very close. So the predicted response closely follows the observed response with some deviations and some noise, obviously. But that would be a high correlation between these two signals, clearly. So we want to extend this, obviously. So let's say this is our chromatic response, and we find a voxel that tracks this quite nicely. In our regression model, we would also have the achromatic predictor time series, which is modeled here as this regressor x sub 2. So x sub 1 models chromatic, x sub 2 models achromatic. And then what we're interested in is actually the difference between these two. So are there voxels in the brain that follow more closely chromatic versus achromatic stimuli? So this brings us back to contrasts. One of the reasons for this being that we're not usually interested in assessing whether one variable has explanatory power. So is there a correlation between chromatic, let's say, stimuli and the bolt response? That's important to specify our model. But when we specify our statistical tests, we're typically interested in one condition and its activation relative to another, in part because there is no meaningful baseline in fMRI. So we want to test whether the contribution of one factor is different from that of another factor. So we're contrasting two conditions. So that's basically saying we're testing the hypothesis that the parameter, the regression parameter beta, for one condition is larger than for another condition in regions that specifically track that one condition. Let's be more specific in this example here. Suppose we want to contrast chromatic versus achromatic to identify regions in the brain that respond to color. That's the idea behind this experiment. We would then compare the beta value for the regressor constructed for the chromatic versus that constructed for the achromatic stimulus. And we would then probe by contrasting these two regressors. So this is the chromatic, this is the achromatic regressor. We would then probe whether one regressor's contribution, namely chromatic, is significantly different from that of the other. And that will give us regions in the visual cortex that are significantly associated with color vision in particular. And the regressor we construct, therefore, is we are comparing beta 1 to beta 2 by setting a contrast weight of +1 for the first regressor and -1 for the second regressor, and zeros for all other potential regressors in our design matrix. Zeros because we're not interested in their contribution to this comparison. We can consider contrasts now in relation to the design matrix that we typically get as an output from any fMRI statistical software package, such as SPM. So this is an SPM output. So we have a design matrix here with our regressors of interest and then regressors of no interest, such as motion parameters and others. But let's have a look at regressors of interest first. So let's say we want to model simply the signal change for the first regressor. This would be, in a sense, comparing the first regressor to baseline. Here what we would do is we would simply set this to 1 and then look at, and then set everything else to 0. So we set zeros for all of these other regressors here. This would indicate that we're just interested in the signal change of the first regressor. This might not be a very interesting comparison. Sometimes it's used to sort of as a manipulation check to look at all task-related activity. So that would be 2 regressors in our case relative to all to baseline, to see if we get things like the canonical attention network that activates during this sort of manipulation check regressor. Typically, we want to compare 2 regressors to each other to identify regions that are specifically activated in one condition relative to the other condition. So in our case, this would be chromatic pictures relative to achromatic pictures to see, to identify regions that are involved in color processing. But you could think of this working for any kind of task. So I'm just generally demonstrating comparisons between two regressors. And we would set the following contrast weights. Since our first regressor is in column 1 and our second regressor is in column 2 for both runs, we would then set these contrast weights to 1, 0, and -1. So these are the contrast weights to compare regressor 1 to regressor 3 in this current design matrix here. This statistical test would give us regions that are specifically activated larger in condition 1 for regressor 1 relative to for regressor 3. Everything else would have to be set to 0 again, which indicates that we're not interested in the contribution of any of these other regressors in the specific contrast. A contrast, by the way, is simply a t-test. So looking at the statistical activation for one versus another regressor. It's also possible to determine interaction contrasts by looking at the contribution of, let's say, 4 different regressors, and this would be one way to specify an interaction, 1, -1, -1, 1. But there are other ways to do so.